When you are asked to explain absolute zero, don't just go and memorize concept from your textbook. The word absolute there means something. It means that there is a zero that is not absolute. Now let us take eyes, for instance. If this is your eyes, do you see these eyes as a solid? If you are still thinking that eyes is a solid, you need to think again, because close observation reveals that eyes is a mixture of solid, liquid, and gas. The evidence is clear. When you handle eyes, you will see liquid water on the surface of the eyes, right? The same eyes, you will see vapor, water vapor coming out from the eyes. What we call eyes is actually a mixture of 3 states of matter, meaning that the 0 degrees Celsius we assign to eyes is not actually the temperature of ice block alone. It is called the triple point of water, because that is the temperature at which water exists in the 3 main states of matter: solid, liquid, gas. Now, this particular 0 degrees Celsius is that zero that is not called absolute. Remember, entropy means the degree of disorder of a system. This is solid. When it changes to liquid, entropy increases because the degree of disorder in liquid is higher. Solids are well ordered. Now, when this liquid evaporates, the degree of disorder becomes highest at a gaseous level. Why the temperature of ice is not absolute is because in the ice you still see water vapor, and water vapor is at its highest entropy. In the ice you still see liquid dropping, and liquid is at an intermediate entropy, and then you see your solid. For the temperature of ice to be absolute, it means that the whole ice will become practically solid. There is no trace of water there, and there is no trace of water vapor. Now, what is an absolute zero? An absolute zero is a temperature at which the entropy becomes zero, where no gas or liquid exists. Now, let us redefine this by observing Charles' law graph. According to Charles' law, the volume of a given mass of gas is directly proportional to its absolute temperature. And this is Charles' law graph. This is temperature axis, and this is volume axis. According to Charles' law, as volume increases, temperature increases. Meaning that if you are heating a particular gas, the volume will increase. It will try to expand, right? And if you are cooling a gas, you are reducing the kinetic energy, and the gas will eventually form liquid, and from liquid to solid. Now, this is 0, and there is a particular value of volume at which the temperature will start increasing. Now, this graph represents initial volume of V here, increasing as temperature rises. Now, if you reproduce this temperature axis backward and trace this same graph backward, there is a place where it makes an intercept on temperature axis. This place is where the volume becomes 0. You can see at this point the volume has reduced to 0, right? This temperature value at which the volume of a gas becomes theoretically 0 is called absolute 0. And the value on Celsius scale is minus 273 degrees Celsius. And on Kelvin scale, it is 0 Kelvin. So, according to Charles' law, the absolute 0 of a temperature is the 0 where no volume exists. And how do we relate it to the formal definition of absolute 0 that says the temperature at which entropy is 0? The two are relatable. When entropy is 0, it means no gas is existing, right? It is just solid. And when no gas exists, there wouldn't be any volume to occupy, right? Because gases occupy volumes. So, in fact, this is the most straightforward definition of absolute zero from the Charles' law graph, that it is the temperature at which the volume of a gas becomes theoretically zero. But do we in real life have absolute zero? It is impossible to obtain. Yes, although scientists have tried to get a near absolute zero, but it is impossible to attain. The only gas that can attain absolute zero is known as ideal gas and not real gas, because ideal gases are not even compressible, and according to one of the laws of thermodynamics, entropy of the universe cannot become zero. The universe keeps expanding. If you found this lecture useful, click on like, comment, share this video, and subscribe to our YouTube channel. Bye.